Alright, this is exam 3 from fall of 2008 for Physics 101. It says an object at rest begins to rotate with a constant angular acceleration. If this object rotates through an angle theta in time t, through what angle did it rotate in time 3t? Well, we know that theta is equal to omega naught t plus 1/2 alpha t squared, but omega naught is 0, so theta is just 1/2 alpha t squared. If it rotates through an angle theta in time t, if we triple this t, then this becomes 9 theta because it's squared, so the answer is B. A tire placed on a balancing machine in a service station starts from rest and turns through 1.59 revolutions in 1 second. So that is theta equals 1.59 revolutions. I can convert this in 1 revolution. There are 2 pi radians. And I see that is equal to 10 pi radians. The time is 1 second, and we want to know its alpha. We also know that omega naught is equal to 0 because it starts at rest. So we say theta equals 1/2 alpha t squared. So that is 10. It's going to just be 10 radians. 10 radians is equal to 1/2 alpha times 1 second squared. That is 10 divided by a half divided by 1, which is 20 radians per second squared. It says a tire 0.5 meter in diameter is placed on a balance machine where it is spun so that its tread is moving at a constant speed of 30 meters per second for 10 seconds. Small stone is stuck in the tread of the tire. What is the acceleration? The only acceleration is the centripetal acceleration. This is equal to v squared over r. Let's see, the speed is 30 meters per second. That's squared divided by the radius, which is 0.5 meters. And that gives me the acceleration, which is 1800 meters per second squared. That's the centripetal acceleration. Alright, a certain light truck can go around a flat curve having a radius of 100 meters. On a rainy day, the coefficient of static friction is 0.2. What is the maximum speed the truck can drive on the curve without sliding off the road? Well, know that the force due to static friction, that is the centripetal force that keeps the truck on the road. It's equal to mu s times the normal force, and this is equal to mv squared over r. The normal force is just the weight, so mu s mg equals mv squared over r. The masses cancel. We solve this for v. It's the square root of mu gr. That's the square root of 0.2 times 9.8 times 100 meters gives me the answer, which is 14 meters per second, which is option D. If a net torque is applied to an object, the object will experience, it's not a constant moment of inertia, that's just dependent upon the object. It will experience an angular acceleration, it won't experience a constant angular speed, and it won't experience an increasing moment of inertia, so the answer is B. This bar is rotating about point C, right here. What is the net torque? I'll call this torque 1, and I'll call this torque 2. The net torque is equal to torque 1 plus torque 2. Torque 1 is the force, which is 25 newtons, times the moment arm, which is 2 meters, times the sine of the angle. That's going to be sine of 60 degrees because you want the angle between the force and the moment arm, and that's this angle. Now this force will cause a clockwise rotation, so this torque is negative. Likewise, this force causes a counterclockwise rotation, so it's positive. And that's the force, which is 30 newtons, times the moment arm, which is 4 meters, times the sine of 45. And that gives me the answer, which is positive 42 Newton meters. Because it's positive, that's going to be counterclockwise. So the answer is C. It says a solid sphere has a mass of 200 kilograms and a radius of 2 meters. It accelerates up to an angular velocity of 1 revolutions per second with an acceleration of 0.02 revolutions per second squared. What work is required to bring the sphere up to this speed? Okay, well, the work is equal to the kinetic energy of the sphere, which is 1/2 I omega squared. So we need to know what I is. If you look on the table that's provided, the moment of inertia for a sphere is 2/5 mr squared. using a mass of 200 kilograms and a radius of 2/5, 200, 2 squared. This gives me the moment of inertia, which is 320 kilogram meter squared. Omega, I'm told, is 1 revolution per second. I need to convert that into radians per second. In 1 revolution, there are 2 pi radians, so that's just equal to 2 pi radians per second. So I can put these numbers in. The work is equal to 1/2 of 320 times 2 pi squared. And that is equal to 6,300 joules. Be sure when you put 2 pi in your calculator that you square both of these. So this becomes 6.28 squared. Okay, this is I'm going to just draw this. You have a moment arm here, your arm, it rotates right here at the elbow. You have one force that acts up and one force that acts down. These two forces have to provide equal torques in order to hold this in a static position. So I'll call this torque 1 and this torque 2. Torque 1 is equal to torque 2. The magnitude of torque 1 is equal to the magnitude of torque 2. Torque 1 is the force due to the bicep times 0.03 meters. Torque 2 is the force weight of the bowling ball, that's 30 newtons, times the length of the moment arm, which is 0.35 meters. And then the force exerted by your bicep, if you solve this, which is 30 times 0.35 divided by 0.03, is equal to 350 newtons. That's about half my weight. So 350 newtons. See, and this one was A. What are the units for the moment of inertia? Well, moment of inertia is mr squared, so that's kilograms meters squared. What is the moment of inertia for this arrangement of particles? Well, continuing with this equation, it's just the sum of mr squared. So starting down here, m is 1 kilogram times the moment arm, which is 3 meters squared, plus 4 kilograms times 2 meters squared, plus 8 kilograms times 1 meter squared. And that's equal to 9 plus 16 plus 8, which is 33. Notice that this mass didn't come into play because for this mass r is equal to 0. So it includes, or rather, it doesn't contribute any moment of inertia to the total moment of inertia. In a mercury barometer at atmospheric pressure, the height of the column of mercury is 760 millimeters. If another mercury barometer is used that has a larger tube of larger diameter, how high will the column of mercury be in this case? And the answer is this going to be the same height. It doesn't matter about the width. In fact, the pressure is equal to rho g times h. So you see this is independent of the cross-sectional area of the barometer. It's only dependent upon the height. In a swimming pool, assuming the density of the pool to be 1,000 kilograms per cubic meter, what happens to the buoyant force acting on your body as you descend to deeper depths? Well, the buoyant force is equal to the weight of the displaced fluid. Alright? And the weight of the fluid that you displace doesn't change. So the answer is A. Stays the same. See, the answer up here was 33. A boat is carrying a large wooden block which has a density less than that of water. What happens to the level of the water in the lake with respect to the shore when the block is thrown overboard and floats outside of the boat? Okay, this was straight from a concept test. Initially you have a block in the boat, and then you have the boat plus the block floating. As long as the block doesn't sink, then the level of the water is going to remain the same. It's still displacing the same amount of water, whether it's in the boat or outside of the boat. So the answer is C. Air is trapped above liquid water in a rigid container as shown on this figure. If the air pressure above the liquid is 1 atmosphere, so P naught up here, is 1 atmosphere. Determine the pressure inside a bubble 9 meters below the surface of the liquid. So P is equal to P0 plus rho GH. That's equal to 1 atmosphere, which is 1 times 10 to the 5th pascals, plus rho GH, which is 1,000 kilograms per cubic meter, times 9.8, times 9 meters. And that is equal to 1.9 times 10 to the 5th pascals, which is 1.9 atmospheres. So the answer here is A. For number 14 is A. Boat has a volume of 3.2 cubic meters. If the boat has a mass of 500 kilograms, what is the total mass of cargo that the boat can carry without sinking? Well, as I've already said, the buoyant force is equal to the weight of the displaced fluid. That is the fluid that the boat displaces. Alright, and in this case we'll assume that it goes all the way down to the top of the boat, so that it displaces 3.2 cubic meters. Right, that's the maximum amount of water that it can displace. So this is going to be the density of water times the volume of the boat. That's the mass of the displaced fluid times gravity. And so this is 1,000 times 3.2 times 9.8, which gives you 3.1 times 10 to the 4th newtons. Alright, if we divide this by 9.8 to get mass, you get 3,200 kilograms. Alright, so that's not the answer though, because you have to take into account the mass of the boat. So 3,200 minus 500 is equal to 2,700 kilograms. So that's how much cargo you can put in the boat. That's option C. You squeeze the end of a garden hose to make the cross-sectional area smaller. According to Bernoulli's principle, what happens to the pressure of the water passing through this smaller area? Okay, well, we know from Bernoulli's principle that pressure plus rho GH plus 1/2 rho V squared, that this is all equal to a constant value. So, assuming that H is constant, if we we also know from the equation of continuity that the area times the velocity also remains constant. So, if we decrease the area, that increases the speed. So the speed of the water increases. And here, if the speed increases, then the pressure has to decrease. Right? So when you make it smaller, the pressure of the fluid going through the small area is actually going to decrease. So the pressure decreases. That is option C. Alright, this figure shows a hydraulic lift. Force 1 is magnitude of 100 newtons and area 1 is 0.01. The area 2 is 1 meter squared. What is the weight of the truck? Well, this is from Pascal's principle. The pressure in, which is F1 over A1, is equal to the pressure out, which is F2 over A2. And I want to know what F2 is. That's the weight of the truck. So F2 is F1 A2 over A1. That is 100 newtons times A2, which is 1 square meter, over 0.01 square meters. And that gives me the answer, which is 10,000 newtons, or 1 times 10 to the 4th. This figure shows a barometer. If the barometer is filled with water, what is the height when the pressure is 0.2 atmospheres? Well, here the pressure inside is 0, so and the pressure out here is 0.2 atmospheres. And that pressure, 0.2 times 10 to the 5th pascals, is equal to rho times G times H. I want to know what is the height. This is equal to 1,000, that's the density of water, times 9.8 times H. And then if I solve for H, I find that it has a height of 2 meters. That's option C. Alright, a glass cylinder is stuck inside a hole in an aluminum block. What is the best way to get the glass cylinder unstuck? So I have an aluminum block with a glass cylinder. So this part is aluminum and this part is glass. Now we look at the coefficients of linear expansion. The the coefficient for glass is smaller than the coefficient for aluminum. That means if I heat it up, the aluminum is going to expand at a greater rate than the glass. So if I heat this up, the hole is going to get faster at a bigger rate than the glass cylinder gets bigger. So heating both the glass and the aluminum pieces is the only option here that will help. So that's option A. Two identical cylinders at the same pressure contain the same gas. If A contains 3 times as much gas as B, which cylinder has the higher temperature? We return to the ideal gas law, PV equals nRT. It says they have the same pressure. A contains 3 times as much gas as B. Which has the higher temperature? Well, N is inversely proportional to T. So if N is small, then T is big. To keep that constant. If PV is constant, if you make N small, then T has to get big to compensate. So if N is small, T is big. Which has the higher temperature? It's the one with the less gas, and that is container B. Which of these is equivalent to room temperature, which is 20 degrees Celsius in kelvins? Well, a Kelvin is equal to 273 plus the degrees Celsius. So it's 273 plus 20 degrees Celsius is 293 Kelvin. And that's D. Number 22, you have this brass sleeve that's to go over a tooth that has an average diameter of 1.5 centimeters. The diameter of the sleeve is 1.498 centimeters at 30 degrees Celsius. So you need to heat up the sleeve so it fits over the tooth. And then when it cools off, it's going to shrink back down again. And we want to know what temperature must you heat it. Well, we start with this, that delta L is equal to alpha L naught delta T. Delta L is L final minus L initial. My L final is going to be 1.5, and my L initial, that is 1.498 centimeters. And that's equal to alpha, which is 19 times 10 to the minus 6 degrees Celsius to the minus 1 times L naught, which is 1.498 times delta T, which is T final minus T initial, which is 30 degrees Celsius. So we solve this for T final, and we find that it's equal to 100 degrees. That's 100 degrees Celsius, which is the boiling point for water. Alright, so the answer is D. A rigid container has a volume of 0.1 cubic meters and holds 10 moles of gas. If the gas is at a pressure of 1.5 atmospheres, what is the temperature of the gas in Celsius? We need to use the ideal gas law, PV is equal to nRT. We have a pressure of 1.5 atmospheres, so that's 1.5 times 10 to the 5th pascals. The volume is 0.1 cubic meters. And that's equal to N, which is the number of moles, that's 10, times 8.314, the ideal gas constant, that's in joules moles per Kelvin, and then the temperature, which is what we want to find. We solve this for T, it's equal to 180 Kelvin, but want it in Celsius. Remember, Kelvin is equal to 273 plus your degrees Celsius, so degrees Celsius is K minus 273, or 180 minus 273 is minus 93 degrees, or minus 93 degrees Celsius, and that's B. Alright, finally, 24, it says a steel tape measure is marked, so this gives accurate measurements at room temperature. If the tape measure is used at low temperatures, how will its measurements be affected? Alright, so here's your tape measure at room temperature. Say it's 1 meter. When you go to really cold temperatures, it gets a lot smaller, or it gets a little bit smaller. So now, you think that a meter is this distance, but it's actually short. Alright, so it's going to measure things to be too large. So the answer for that is B.